Good evening, everyone. Welcome back to NPTEL live session. So today we will be taking up few more further topics, what we have discussed last week. So is there any doubt from the last live session? This platform is open for your queries to be answered. If not, then we will wait for 2-3 minutes more for others to join and then we'll start it. Is there any doubt from the last live session that we discussed?
No doubt, ma'am.
Okay. So we have 9 questions for today's assignment that we will discuss at the end. But initially, I would just give a brief what we have understood regarding the MOSPAR spectroscopy so that everything is in line. So initially, so when we were talking about different electromagnetic radiations, which have a specific role in each and every spectroscopy. For example, in NMR, we use radio frequency. For EPR, we use micro radiations. For IR, then IR radiations, so on and so forth. Similarly, for MOSBAR, this spectroscopy involves the most energetic, like the radiations which are having the maximum energy, so-called gamma rays, that have been used to provide the details or the information about the certain compounds and certain complexes. So in this MOSBAR, we saw that the necessary condition, or I would say that prerequisite is, in NMR, we see the splitting or the transition from one state to other state, the energy states, it's in between the same I values. Like if it is I equals to half, then because of the two different MI values, that would be transition between the same nucleus spin state, because the energy between these two states that is matching what we are giving from the radio frequency. Whereas if we talk about the MOSBAR, if I have two states, I equals to half, it's ground state, I equals to 3/2, it's excited state. Say for example, iron 57 nucleus that we discussed last time. So here, when I'm having this kind of splitting, -1/2 plus 1/2, and here it would be having 4 states plus 3/2 plus 1/2 minus 1/2 minus 3/2. So depending upon what I state we have, we will be having MI values going from that particular thing. Say for example, if it is 3/2, MI values would be plus 3/2 plus 1/2. It's having a difference of 1. So it should be having a difference of 1 up till it goes to the minimum value. So the difference between this 3/2 to 1/2 is 1. Then again, if I'll go, this will come as minus 1/2 and minus 3/2. So for I equals to 3/2, we have possible 4 mi values. Similarly, for I equals to half, we have plus 1/2 and minus 1/2, two states. It happens in the similar case when it's a similar way when we talk about the that quantum numbers that we have. Say, for example, L value is 3 for F orbitals, or L value is 2 for D orbitals. So when we talk about the D orbitals, the L value is 2, that's a quantum number. But when I'm talking about the ML values, it goes from +2 to -2. So it would be having +2, +1, 0, -1, -2. Similarly, in case of these nuclear spin states, we have to consider the MI values. Similarly, when we are taking the L quantum number, we are having ML values. So it goes in similar fashion. Here, when we are starting with one particular thing, it should be having difference of 1. The similar way we are having for secondary quantum numbers. And this way we know that how many splittings could happen for a particular nuclear spin state. Now the main point was, in NMR, we can split, or we can have a transition between in presence. This is happening in presence of magnetic field, right? So this splitting will only happen in presence of magnetic field because interaction starts happening, whereas these states will remain as such or degenerate in absence of any magnetic field, right? Now, the transition in between the same nuclear spin state will happen only when it is lying or matching with the radio frequency range. That energy is very small. So this energy, if I'll talk about, this is energy E1. And if you compare in between the different nuclear states, the energy is delta E2. So delta E2 is very, very large compared to the delta E1, because radio frequency comes at the very, if I'll talk about the electromagnetic radiation, the trend goes like gamma radiations are at the one end, that's the maximum, or more than gamma, it's cosmic rays also, but we don't generally talk about them. Here we are talking about the spectroscopy, what the radiations that we can provide them. So maximum, we are giving the gamma radiation. So maximum energy among all the radiations, and here at the other end, we have radio frequency radiations, right? So which is having the minimum energy. So you can understand like what is the range that they are going. Similarly, when we are having this much amount of energy that we are providing, then only the transition from one nuclear state is happening to other nuclear state, and in between those states will happen when we are giving the radio frequencies. So up to this point, is that clear?
Clear, ma'am.
So our main motive was, we started with this Morse power. We understood that, okay, it is happening in between different nuclear spin states, different I values. That is clear. Now the second point is, for emitting those gamma radiations, that's a very high energy, high amount of energy, we require a source which can give to a sample, and sample can absorb that, and we could see a peak shift or any difference, or for that matter, we could see something in spectra, and we could differentiate between two different compounds or nuclei or complexes. Now, the condition for Morse power to happen, or that whatever the radiation it is giving, that it is emitting, it should be matching with the same radiation it is absorbing, then only they would be in same resonance, right? So the source and sample needs to be the same. That was the condition. And then when source and samples are same, we saw that if I am having, say for example, here I am having two states, the ground state and excited state. This is for my source. This is in case of source. And here, this is the excited in ground state for my sample, right? So when my source is already in an excited state, it will emit energy. It will come back to the ground state, and therefore it will emit energy as gamma rays. These gamma rays would be absorbed by the ground state of the sample, and they will go and get excited. And then there would be some spectra would be visible because of the absorption that has happened. But generally, because of these high gamma rays, they do not have a similar kind of energy. Like the emitted energy and the absorbed energy is not same because of the recoil energy. We understood this concept last time, that when we have a high amount of energy, for example, when we are using a gun and when we are shooting, so because of the gun and this much force we are giving, this much energy with what the bullet will go out, because of that some of the energy converts to or lost in kinetic energy that is in opposite direction. That's why when the bullet goes in upward direction, our shoulder goes in backward direction because of the recoil energy terminology. And because of this recoil energy, say for example, X amount is being emitted, that is gamma radiation. But from the X amount, which was expected to be absorbed by the sample, some amount is lost in the kinetic energy. So now what it is being emitted and what it is being absorbed, it is not matching. There is no resonance. Therefore, actual absorbance does not happen because the ground state, since we are saying the source and sample are same, when source and sample are same, their ground and excited state would be the same. Like if it is first step and it is second step, the energy required is delta E. So for absorption also it requires delta E only. But if some amount of energy has gone into kinetic energy, then delta E say that we are getting lesser amount. So absorption won't happen because the transition will only happen when there is a proper or quantized energy pattern we are following. We cannot just have a lesser amount or a higher amount and then we will expect that we'll go to the same excited state. No, either we'll ended up having the down one, or if it is more, then we'll go to another excited state. So that's the concept over here. So to remove this recoil energy, what it was suggested that the sample, this is our sample, both are same. That's why I'm making it in a similar color. So they were being fixed in a solid matrix. Because of their movement only, the recoil energy was happening. So they were being fixed in a matrix. And because of this, we got the recoil-less energy. We can't say that completely it got zero, but there is like minimal amount of recoil energy was there. So because of this, now we are having the absorbance, the emission of the energy is equal to the absorbance of the energy. And since we have a source and there would be a detector, and when detector is not able to see any peak or any energy being transmitted because X amount of energy is being lost from here and X amount of energy is being absorbed here. This is emitted energy and this is absorbed energy. When both are same, then no transmission has happened, so the detector won't be able to see anything. So in the transmission, we know that we have this transmitted thing. So transmission will be 100%. In case when we have no absorption, and it would be zero, like everything has been absorbed and nothing has been transmitted. So the graph would be like just this matching or overlapping with the x-axis. So we won't be able to see any shift, any peak, because it is this constant line. So that for avoiding this situation also, Doppler effect comes into picture. So Doppler effect says, okay, we understood that we have fixed our sample. We have fixed our source also. And the detector, that is also fixed. Okay. Now, what really happens here, what we do, we provide a kind of, like we can say that's a wheel. Or we can say it's a tire. So we have given the tires to the source. Now it can either move towards the source or it can go away from the source. Because of this movement, going towards and away, that's positive velocity and minus velocity, the negative or positive side is only defining the direction. So when that is happening, we will be starting seeing the variation. For example, the graph then becomes, this is transmitted and this is, now the graph would be velocity millimeter per second. That's actually an energy function. So the main mass bar spectroscopy graph will come like this manner. Now earlier we were having a case where we feel that, okay, when it is moving and the emitted energy is exactly equal to the absorbed energy, so it will not move. So if it is not moving, that V equals to 0. The first point it is not moving, they were in static condition, the earlier one. So we won't be able to see any transmission. So that's why the transmission is 0. That's the first point. Now, if it moves towards this source. So it would be having certain absorption and certain amount of transmission. So therefore V1 is here. And if the 100 total transmission is here, this particular pattern. So if it is moving even away from this sample, like no absorption, anything is happening because they do not overlapping with each other. So that 100% transmission will happen because absorbance could not take place. So V2 would be at matching with the 100% transmission. And similarly on the left side direction, we will get minus V1 here and minus V2 here. Now, if you will jot the points, we will be able to get a shape, a curve like this way, where it is forming a curve like this way. And this is actually what we see in different spectra. Like variation is happening. So this is a kind of MOSFET spectra that we expect to be seen, and the variation also. So up to this point, we saw yesterday. And we also talked about the isomeric shift. So in isomeric shift, what we understood, it is been denoted as delta, and its value is being given as 4 by 5 pi ZE square R square delta R by R psi 0 sample minus psi naught source. So don't get worried about this whole equation. The main factor for the isomeric shift, that what we are actually expecting and where it got shifted, that is the kind of shift we observe. Why it happens, that I will tell you now, and earlier also I talked about. So this is the first factor, and this one is the second factor. Why? If I'm taking, say for example, why am I talking about the shift? Shift means we are expecting the graph to be like this way. But what we saw, it moves to this direction. So therefore, there is a shift from here. From the original position, there is a shift from somewhere. It happens when the electron density perturbation and some kind of shielding effect is happening. So the two major factors, the delta R by R, that's a derivative of the radius. That means this delta R is the radius of the nucleus in the excited state minus radius of the nucleus in the ground state. So it has been found in case of iron, this value to be negative. That means in excited state, the radius becomes contracted, that nucleus becomes contracted, and therefore the radius of the excited state becomes less. And this value is negative for iron and positive for tin, the another MOSFET active nuclei. And why am I saying the source is this value, this electron density? This is nothing but this S electron density, which we are expecting to be present in the nucleus or penetrating into the nucleus. So because the source is common for iron in +2, iron in +3, or for iron any complex or compound for that matter, the source would be constant, that is coming from the cobalt. So that's why this electron density coming from the source would be constant. The only variation we would be able to see in the sample. Like because the sample is varying, be it in oxidation state or kind of ligands or environment it is having, that would be different. So the S electron density penetration into the nucleus of the sample, that would be varying depending on different parameters. So these two parameters, they are main, which are affecting the delta. Now, one more thing. When I'm talking about the S electron density of the sample, why is it actually getting affected? This S electron density in the nucleus, its penetration or its presence, whatever you want to say, why it is getting affected, and who is affecting it actually. So if I will take a case of iron in +3, say for example, I'm taking iron in +3. So if I will draw its electronic configuration, firstly, it is 3d5, 4s0. So that's the first case. If I'm taking just iron metal, so it would be 3d6, 4s2, right? And there would be some 3s electrons also, 3s2, 3p6. These are also there. Here also 3s2, 3p6, 3d5. So if we are not considering this 4s and taking an iron 3 case, we have 3s2, 3p6 fully filled, and 3d5. Before this, it is called core electrons. Whatever the noble gas configuration it is following, it is having core electrons, and these are called as valence electrons, which will be participating in your bonding or something like that. Up to this, it is clear, like what are valence electrons and what are core electrons. Valence electrons, which are outside and which are involving in kind of bonding and interactions. The core electrons, they do not generally participate in that kind of interaction. So is that clear?
Clear, ma'am.
So now, if you will see clearly, here, if I'll talk about the 3s and this 3df. So now we are going to make this radial density wave function that we had it, radial distribution wave function. And here we draw the distance from nucleus. So if we will draw for the 3s, since 3s is expected to have 2 nodes where the electron density would be 0, and it starts, as I said, it starts from here, it is having some density. So it looks like this way, right? And if I'll draw for 3D, it will be going from 0 and going like this, right? Now, if you will see, this is for 3D and this is for 3s. Here, there is a certain common area. If I will draw over here, there is a certain common area, which I'm highlighting with this dash, where it is having both 3s and 3d electron density, right? When this is the case, that means both want to be closer or having an interaction with the nucleus, but some way or the other, one is affecting or shielding the other. For example, if this 3s, as we said, only the s electrons, they can penetrate into the nucleus. So there is a nucleus, there is a s electron density, and it wants or it is penetrating, as we saw from the graph. But if at all there is a 3d electrons over here, as I draw here with the red pen. Say for example, now 3d has come. So the interaction between now s and nucleus has been decreased, because somewhere in between the obstacle has come. The 3d electrons are trying to de-shield it from the nucleus. It is to shield it from the nucleus. Say for example, if my nucleus is this one and my s electron is this one, and in between something else is coming in between. So the third party is coming in between, which is increasing the distance between the two. It is shielding it to have more interaction from the nucleus. So that effect is known as shielding effect. Why we are even worried about it? Because our delta, that isomer shift is dependent on the s electron density of the sample. This s electron density means how much it is penetrating or interacting with the nucleus. So if in between d electrons are coming and increasing the distance or shielding the s electrons to have an interaction with nucleus, this value would become less. And when this is less, this would become less. So depending upon different metals in different oxidation states and different environment, they would be having different kind of shielding effect of the d electrons on the s electrons, and that will affect your isomeric shift. So depending upon how do we differentiate different complexes? That's why in Rn case, when we have Rn plus 2, Rn plus 3 plus 4 or something like that, be it in metallic state or Rn 0. So when we have to compare on what grounds we are going to say that this complex is having Rn 0, this complex is having Rn plus 2, that is only when we get to know information about the delta. And delta is dependent upon the s electron density, and that s electron density is getting shielded with d electron density. So metal is that 3D metals are mainly having the 3D electrons, right? So if they are more or less in number, they would be having more or less shielding effect on the s electron penetration, and that will ultimately affect your delta. I will explain it with the example. So as per we understood that shielding effect is most important parameter in calculating or determining the isomer shift, and this depends upon the d electrons in case of iron, because in case of iron 3s to 3d, they are more intact with each other when we are mainly talking about the iron or 3D metals. So these metals or these electrons would be the one, because 3p6 is anyway going to be the filled. So in case of, even though 3p6 is also there as a valence electron, but in case of all the 3D elements or all the transition elements, the 3p6 is going to be constant. So this is not going to be changed. This is constant. But if I'll talk about the d electrons, depending upon different oxidation state, the value would be different. For example, if I'll start with iron in 0, that would be having 3d6, iron in +1, that is 3d5, iron in +2, sorry, that is 4s2, or if we remove, we have to include, so this is 3d8, if we are talking about, because the s electrons goes, as we saw last time, that energy barrier goes away whenever it is in metallic form or when it comes to the complexation. So the first filling happens in the d electrons over the s electrons, and iron in +1 would be d7. This is d6. Iron in +3, it's 3d5. Iron in +4, it's 3d4. So this is maximum I'm showing you. So you can see 3p6 would be constant in everywhere. And we are talking about 3s2, that screening of the shielding effect on the 3s2. So we are seeing this shielding effect on the 3s2. So if you will see, this factor is constant in everywhere. So this is not going to affect anything. Like for iron, iron +1, 2, 3, 4, the 3p6 is constant. So it is not going to have any effect. Even if it is shielding, it is constant for everything. So relatively, we don't see any difference when we talk about the 3p6. So that factor is gone. Now talking about what is the factor which is actually affecting it, it's the d electrons. If you will see, here more d electrons compared to here. So this iron in 0 state and iron in +4 state, which one you feel is going to have more shielding effect on s electrons? Is it iron in 0, which is having d8, or iron in +4, which is having d4? Which one is going to have more shielding effect on s electrons? Shielding effect you can understand in that way. For example, if I have to reach to a certain distance from one point to certain point, I have to reach it. Now earlier there was nobody in between me and the door, but now firstly two students came and sat in between, so I will be having more shielding compared to earlier state when there was nobody in between me and the door. So it was easy for me to walk from one place to the door. But the second condition, when two students came and sat there, or say for example, iron in +4, d4 you can consider 4 electrons, 4 students. So 4 students came and sat in between. Now 4 students came, so it has increased the distance from me to the door, and that the probability or that ease of me going easily over there, then now I have to cross those students and then I have to go there. Now the next case is iron in 0. Now, if you consider that in between me and door, now 8 students are there. So obstacles have been increased and I am feeling more shielded, because I can't even see the door, or I'm feeling more trouble in moving from here to there at that point, because of the number of students or the electrons, if I would say, the d electrons have been increased. So what, according to you, if I have iron in 0 or iron in +4, which one is going to have more shielding effect on the s electrons? Is it d8 or is it d4?
D8, ma'am.
So this concept is clear now, how we are looking at the shielding effect. So this concept is clear now. This is, because number of d electrons is more, the shielding effect would be more. So that is going to affect the s electron density. Now we found that, okay. Now we found that key more d electrons, more the shielding effect. So that's a very important factor that you need to remember. Now, what happens when d electrons is there and more shielding effect is there? When more shielding effect would be there, that means there would be less electron density, s orbital electron density penetrating into the system. So the psi square, which is our s electron density of the sample, that would be now less. Is that clear?
Clear, ma'am.
Not many electron density or the s from the s orbital could penetrate into the nucleus when this value is less. Now you consider the whole formula of delta. I will not write all the constants. We have some constants over here, which is for everything. The main factor delta r by r and this psi 0 square of the sample. So earlier case, we know that this value is also constant, but just that is negative. And now my psi 0 value is also less. So this delta value would be negative, but in less. So if I'll consider now two cases, iron in +2, iron in +3. So this +2 would be having D6, +3 is having D5. What do you think that delta value is more negative related to the other one?
Three D 6, ma'am. Fe plus 2.
So if we have more negative,
3D 6, ma'am. Fe plus 2 more negative.
I'll explain it one more time. So 3d6 more d6 is there, more would be the shielding effect. If shielding effect is more, this s electron density would be less, and compared to 3d6 d5 would be having more s electron density. This is clear?
Clear, ma'am.
Okay. Now delta r by r is negative. That is for both the cases, because it is like any nucleus which is having the excited state radius that would be lesser compared to the ground state. That happens for every metal in any oxidation state. So if I have, say for example, now in first case, this is A and this is B. A is having, both are having negative and negative, but A is having less value and this is having more value. So this becomes less negative compared to the B. I understood that because of this less electron density, you were saying that that S electron density penetrating would be more. So depending upon this more, this has to be more negative compared to the isomerism. So this 3d6 will give you more shielding, but the S electron density penetrating into the nucleus, that would be less. When it is less, the delta value becomes less. So for when we have iron in high oxidation state, that is going to give you more negative delta value. Now is it clear? Because do not get confused. Firstly, we do not have to memorize anything. This general statement I'm making when we have looked into many examples. So firstly, you have to see the oxidation state, and oxidation state, from there you calculate the number of d electrons. If your d electrons is more, the more electrons are there, that will shield your s electron density. If more d is there, this psi value would be less. Once this is less and this delta value is already negative, we are talking in negative terms. So when something is less negative, that would be coming towards more positive side, because it's a relative term. So if I am having here 0 and here it is -1, here it is +1, right? So the iron, I said iron in +3 is having more negative delta compared to iron +2. So this more negative delta compared to this +1, here it would be iron +3, here is iron +2. So we will be seeing a shift like here. So one peak will come here, this is for iron 2 and this will come for the iron 3. Now it is clear? So this is a relative value. This is not like, it could be in positive also. Say for example, if I'm taking 0, 1, 2. And if now I have to say that which one is iron +3, which one is iron +2, can you please tell me? So out of this 1 and 2, Yeah, you were saying something.
I don't know, ma'am.
Here, see, we need to just remember or understand this point that we are saying when the oxidation state is more, it would be having more negative value relative to the other. This is clear? So more negative means if I have iron +2 here, so more negative matlab it has to be lesser compared to the iron 2. So more negative, you can consider that it is less in value, right? So iron +3 would come at this +1 and this will come as +2. So it does not depend upon, we are talking about the minus sign over here. We are talking about which is less compared to the other one. So iron 3 plus, be it on the positive side, on the negative side, it would be always on the left side of the iron 2 plus. Is that clear now?
Clear, ma'am.
Okay. Now, if I have one example that we are taking, say for example, now I'm saying iron +2, iron +3, iron +4. So this is having 3d6, 3d5, 3d4, right? And here you need to tell me which one would be on the more left side, that means more negative side. This is 0, this is towards negative, this is positive. Negative positive is not, I'm talking about regarding the values. Values could be positive also, but negative and positive is only talking about in terms of which one is more or less compared to the other. So there is a relative term, you need to understand that. So if I'm having, if this I'm saying A, this I'm saying B, and this I'm saying C. As we said that more the oxidation state, how the delta value is going to affect. Which one is going to give you more value compared to the other? Which one would be on the positive side?
Fe2 plus goes to positive side. Fe plus 4 goes to negative side.
And Fe3 plus?
What, ma'am?
Fe3 plus?
Fe3 plus is in 0 position.
Not, we can't say 0 position, but yeah, in between the two. So you're right. When we have more oxidation state, that would be having less electrons, d electron shielding. When d electron shielding is less, delta value becomes more negative. So it would be on the, C would be on the more negative side, and Fe2 positive, because its oxidation state is less, it would be on more positive side, and 3d5 would be in between the two. So now this is clear, like how we calculate and how do we see the delta value?
Okay, ma'am, clear.
Okay. Now we will take up the second point into consideration. So first we have said that effect of oxidation state on the delta, that is isomeric shift. And this we got, the result is, general result is, if all the parameters are constant, result is, if I'm saying all the parameters for everything, like temperature, coordination, everything is constant, and all the oxidation state is varying. So here we say that more oxidation state, more negative delta value, that is more towards left side. So that's a general statement. If you have a multiple choice options and questions, so there you can just think about, like, if I have a metal, all the metals are same and their every other parameters is same, but there one is having more oxidation state, that will give you more delta negative. Delta is going towards the left side compared to the others. So this factor is clear. Now, when we move